Good morning, everyone. Uh, I'm Mansi Padave. I'm a postdoc at University of California, San Diego, working with Karen Sandstrom. And today I'm going to be talking about probing early feedback and massive star signatures in M51. So let's dive in. So massive stars and these young stars, they basically affect their environments in natal clouds as soon as they're born. And before any supernova goes off. So you have they drive stellar winds. There's photoionization, radiation pressure. These are constantly driving and shaping the expansion of H2 regions and also dispersing their parent natal cloud, molecular cloud. Now, trying to quantify how each of these feedback mechanisms is affecting the ISM or is shaping the structure of the ISM involves doing some relative contributions of each of the feedback terms, and it would be great if we also have some coverage on how molecular cloud energetics work so that we can map each of these together. Now, with JWST, it has been possible to get some molecular H2 energetics with the wavelength coverage that it provides, as well as a very high spatial resolution, which is what we have with the JWST Whirlpool Galaxy Treasury. Now, this is kind of interesting because here we have M51. We have mapped the inner disk of the M51 in almost every filter of JWST with NearCam and MIRI. I'm showing the MIRI maps on the top here. And then we also have spectroscopy with NearSpec and MIRI MRS for three regions, Northeast, East, and the Southwest Strip, that provides us access to the full H2 ladder, rotational vibrational ladder, that gives us a picture of how molecular clouds could be dispersing. Now, just JWST alone cannot provide us information on how feedback is affecting the ISN because it does not have the entire wavelength coverage, and that's where Keck is ideal. So for this work, we used Keck KCWI and obtained spectroscopic follow-up for these three regions in the lower resolution, the BL plus RL grading, that provides us the full spectral coverage from 3600 to 10,000 angstroms. And this is basically where we are covering the key ISM diagnostic lines that give us access to photoionization, the temperature, density, pressure, Wolf-Rayet signature. So basically most of the feedback stuff. On top of it, KCWI also has this amazing high resolution mode. So we use the BH3 and RH1 gratings to get access to the kinematic information. So with this, we now also have handle on the mechanical energy input from stellar feedback. So together, the Keck plus JWST spectroscopy is now setting the stage for a 0.3 to 30 micron view of H2 regions in a nearby galaxy. Now, this is kind of exciting because now you can see there's this plethora of information here. So we're going to start seeing what all we get here. So I'm just marking where the Keck coverage is, and this is all JWST. And then, of course, I'm marking the hydrogen series. So we have Balmer lines, Paschen lines, bracket lines, and this Humphreys line also that pops up in the spectra or the coverage here. Then zooming in on the Keck section, of course, the key ISM diagnostics, oxygen 3, then oxygen 2, then we have nitrogen sulfur lines here, some stuff here. So a lot of information and ionization and H2 region or ionized gas diagnostics. And then on top of it, I will also mention JWST provides the full H2 vibrational ladder. Some of the lines I've noted here, as well as PAH or polyaromatic hydrocarbon features. So, now we have set the stage, but today I'm just going to focus on what we are currently, some preliminary results on what we're seeing with our Keck observations. Just to note, like this is, as I said, this is preliminary. You can see a lot of skylines here that need some further analysis to get rid of these, but we'll still try dive straight in. So I'm showing for one of the regions, the Northeast region, because we have the high resolution mode that allows us to make moment maps. So I'm showing H alpha moments. So this is moment 0, which is in the integrated flux, moment 1, which is line of sight velocity, and moment 2, which is velocity dispersion or proxy for turbulence. And as you can see here, the contours are representing where majority of the H2 regions are, or the H alpha fluxes, and the velocity peep here looks pretty consistent with what you'd expect for kinematics. along where the contours are, as well as dispersions of 10 to 30 kilometers per second, which is consistent with turbulence. But of course, what catches the eye is this top left panel, this patch that is showing dispersions of really high dispersions over 40 to 60 kilometers per second, and this strong velocity gradient. Further analysis of this showed that we are basically seeing multiple components, which I have not fit here, but at least you can see two, or if not, at least two, if not three components along the line of sight. And what is happening here, that if you go to HST or the JWST cutout of these regions, so showing where these are, and this is the Keck field, you can kind of see that there's this cavity of H alpha. This is the H alpha. This is 11.3 pH emission. So you can see that there's this cavity that seems like there's some kind of expansion or some bubble that has been created. So it's possible that we could be tracing this shell expansion from this neighboring H2 region. Moving on, the southwest strip, this is also exciting, which is the region that I've shown on the right. This is the spectra for this extracted in this aperture. It's kind of oxygen 3 the Aurora line popping up, but still embedded in the stellar emission. All the three regions are selected based on the fact that we can detect these lines here. But what other thing that pops up is this feature of lines, which are classic Wolf-Rayet signatures. So we have helium-2, which is the blue bump, and the nitrogen-3 lines, nitrogen-3 lines. And then looking at the dispersion along this region, it seems like in H alpha, we are seeing that the gas is relatively in a less turbulent environment, the surrounding. But comparing these kinematics to oxygen-3, we're seeing it's more turbulent. Just kind of exciting and something to investigate further. The last region, which is showing the oxygen-3, so here I'm showing the H alpha and oxygen-3 channel maps for the E strip. Sorry, I should have mentioned that it's the E strip. But here you can see some beautiful structures emerging in H alpha on the left and oxygen-3 on the right, and you can kind of see that there are these blobs that pop up in oxygen-3. What we're seeing here that these either they do not have an H alpha blob-like counterpart, or they're basically just morphologically offset from the H alpha structures. Further analysis of velocity components, so taking oxygen-3 and H alpha velocities, and finally we see that these blobs do pop out as redshifted and blue shifted blobs that are kinematically decoupled from the ionized gas emission. So these look like that these could be possible signatures of like some breakout channels or expanding shells or just pockets of localized feedback heated gas. So kind of exciting things that we can probe with this data set. So I circled back to this beautiful view of 0.3 to 30 micron spectra. And I started with saying that the original goal that we want to do is map out how the different feedback components help in or contribute towards the dispersal of molecular clouds. So there's much more to come. Today I just showed some of the key things that we immediately saw in the spectrum. But we're going to do some extinction curve analysis, map out attenuation, and then get a handle on radiation pressure, winds, and molecular gas from this combined Keck plus JWST data set. And with that, I leave you with my conclusions. I have three regions, the three things that I showed with the multiple components probably tracing expansion, the Wolf-Rayet signature, and these offset oxygen-free blobs. And with that, I'd be happy to take any questions.